Welcome to the deep dive. Today, we're really getting into the weeds on a fundamental concept in computer science, the linked list.
That's right. It's one of those core building blocks.
Exactly. And our guide for this is going to be an excerpt from Hello Algo, specifically section 4.2.
A great resource for this topic.
It is. So our goal, our mission today, is to properly unpack what linked lists are, how they actually function, and crucially, why they matter, especially when you stack them up against arrays. We want you to walk away with a really solid, deep understanding that hopefully lasts a lifetime.
And it really addresses a key problem, right, which is memory allocation. Sometimes finding one big chunk of continuous memory which arrays need, well, it can be tough.
Yeah, especially as systems run and memory gets fragmented.
Exactly. Linked lists offer a completely different way to organize data in memory.
And that different approach gives them this flexibility, this unique advantage in certain spots. Okay, let's start right at the beginning. What is a linked list, fundamentally?
Okay, so at its core, a linked list is a linear data structure. Data is in a sequence.
Linear like an array.
Yes,
Yeah.
linear and like an array, but the how is different. Instead of being implicitly next to each other in memory, a linked list is made of individual things called nodes.
Nodes, okay?
And these nodes are connected explicitly. They use references.
References, like pointers.
Precisely. Think of each node as a little container. It holds the actual data, the value, and then it holds this reference, basically the memory address of the next node in the chain.
Ah, okay.
So in languages like C, C++, Bo, Rust, you often hear pointer, which is that direct memory address. In, say, Python or Java, it's usually called a reference. But the idea is the same. It tells the computer where to jump next to find the following piece of data.
So it's less like houses all lined up on one street, which is kind of how I picture an array.
Right, needing that contiguous block.
It's more like a scavenger hunt,
Yeah.
where each clue tells you exactly where the next clue is hidden, potentially anywhere.
That's a really good analogy, actually.
Yeah.
Yeah. The nodes can be scattered all over memory. You just follow the chain of references, clue to clue, node to node.
So where does the hunt start?
It starts at the head node. That's the first node, your entry point into the list.
Yeah.
You have to know where the head is.
And where does it end?
It ends at the tail node. That's the last one in the sequence. And its reference, its next pointer, doesn't point to another node. It points to a special value, usually null or maybe null PTR or
Yeah.
none, depending on the language.
That's the signal, stop here, end of the line.
Exactly. That null tells you you've reached the end of the list.
Okay, but the source, Hello Algo, brings up an interesting point. Linked lists, despite being flexible about where nodes live, actually take up more memory per item than arrays. Why is that?
Ah, yes. That's because each node has to store two things: the data value itself and that reference, that pointer to the next node.
Right, the address of the next clue.
Exactly. An array element just stores the value. So you gain placement flexibility, but each node needs that little bit of extra space for the linking information. It's a classic trade-off.
Space versus flexibility. Got it.
Okay, let's get practical. How do we actually, use these things? How do you set one up or change it?
Well, building one usually involves two steps. First, you create the individual node objects. Give each one its value.
Just making the containers.
Right. Then the second step is connecting them. You set the next reference on each node to point to the node that should come after it.
You wire them up.
You wire them up. So the example in the source is 1 to 3 minus to 2 minus 5 to 4. You'd make 5 nodes. Node 1's next points to node 3. Node 3's next points to node 2.
And so on until node 4's next points to no.
Exactly. And typically, you just need to keep track of the whole list by holding on to a reference to that first one, the head node, node 1 in this case.
Makes sense. You only get the starting point. What about changing the list, like sticking a new node in the middle somewhere? Okay. This is where linked lists often have a big advantage over arrays. Hello Algo calls insertion very easy. And, well, the linking part is incredibly efficient once you know where to put it.
Okay.
So imagine you have two nodes, N0 and N1, currently linked, and 0 points to N1, and you want to insert a new node, P, right between them.
Right in the middle.
You only need to change two references. First, you change N0's next reference so it points to your new node, P.
Okay, so N0 now points to P.
Yep. Then you set P's next reference to point to N1. Now the chain goes N0, P, N1. You've just woven P in.
And how fast is that? Just changing those two pointers.
That operation, just updating those two links, is 01. Constant time.
Constant time. So it doesn't matter if the list has 10 nodes or 10 million.
Correct. The act of relinking takes roughly the same, very small amount of time, regardless of list size.
Wow. That's hugely different from an array where inserting in the middle means you might have to shuffle potentially millions of elements down.
Exactly. That shuffling in an array is what makes insertion ON linear time. It gets slower as the array gets bigger. The O1 linking for linked lists is a major plus.
But there's a catch, right? You said once you know where to insert.
Yes, good point. Finding the place to insert, like finding node N0 in the first place, might still require traversing the list from the head, which could take ON time.
Yeah.
But the actual insertion operation itself, the relinking, is O1.
Okay, clear distinction. Linking is fast, finding the spot might not be. What about taking a node out? Deleting one?
Deletion is also very efficient, the linking part anyway. Also described as very easy in the source. Let's say you want to remove the node that comes right after N0. Let's call that node P, and assume P currently points to N1.
So the chain is N0P, ON, N1. We want to remove P.
You just change one reference. You update N0's next reference to point directly to N1, basically skipping over P.
You just bypass it.
Exactly. 0 now points straight to N1. P is effectively cut out of the list because you can't reach it anymore by following the chain from the head.
And that single pointer change is also.
Also O1, constant time for the relinking.
Okay, so adding and removing elements, especially anywhere in the list, is super fast. O1 for the linking part. That seems like a massive win. But you mentioned a trade-off earlier. Where do arrays fight back?
Right, the other side of the coin. Accessing elements. This is
Yeah.
where arrays really shine. If you want the element at, say, index 5 in an array,
The computer just jumps straight there.
instantly. Because the array data is all together in one block, the computer can calculate the exact memory address of index 5 based on the starting address and the size of each element. That's O1, constant time access. Super fast.
Because they're all neatly lined up.
Precisely. But with a linked list, remember, nodes are potentially scattered. To get to the fifth node,
You have to start at the head.
yep, start at the head, follow the next reference to the second node, follow its next reference to the third, and so on.
You have to walk the chain. So to get to the, I don't know, the 100th node, you'd have to step through the first 99 nodes?
It's exactly right. To access the ith node, you have to perform I1 traversals, following those next pointers. This makes accessing an element by its position in a linked list an ON operation linear time. It gets slower the further down the list you need to go.
That's a huge performance difference. O1 for arrays, ON for linked lists, for access by position. What about finding a node based on its value? Like finding the node that contains the number 5.
That also requires traversing the list. You'd start at the head, check the value in the first node. Is it 5? No. Follow next. Check the value in the second node. Is it 5? No. You keep going.
Just checking each node one by one.
Yep, it's a basic linear search. In the worst case, the node you want is the very last one, or maybe it's not even in the list.
So you'd have to check every single node.
Right, which means finding a node by its value is also generally an ON operation.
Okay, this is making a lot more sense. Linked lists are fantastic for quick insertions and deletions once you're there, but slower for just jumping to a specific spot or searching. Arrays are the opposite. Fast access, slower modifications in the middle.
Exactly. Understanding these trade-offs is absolutely crucial for choosing the right tool for the job.
Let's try and summarize these key differences then, drawing from what Hello Algo lays out.
Sure. So, big picture comparison. First, storage. Arrays need that single contiguous memory block. Linked lists. Their nodes can be dispersed all over memory, linked by references. That's the flexibility advantage, especially when big contiguous blocks are scarce.
Right.
Second, capacity. Arrays usually have a fixed length set at the start. Yes, there are dynamic arrays, but resizing them can be costly. Linked lists offer flexible expansion. Adding or removing nodes is generally straightforward without needing a massive reallocation.
More fluid growth.
Exactly. Third, memory efficiency. This one's nuanced. Arrays use less memory per element, just the data. But you might waste space if you allocate a huge array and only use part of it.
Yeah, that unused space.
Linked lists use more memory per element because you need space for the data and the references. But you usually only allocate nodes as you need them, so you might avoid that large-scale pre-allocation waste.
Different kinds of efficiency.
Right. And finally, the operation efficiency we just hammered out. Accessing by index. Arrays O1. Linked lists ON. Adding deleting, especially mid-list. Arrays typically ON to the shifting. Linked lists O1 for the linking part.
It really drives home that there's no single best data structure. It
Yeah.
totally depends on what you're doing most often. Lots of additions, deletions, maybe a linked list,
Yeah.
lots of random access, probably an array.
Precisely. Choosing wisely based on the expected workload is key to performance.
Okay, so we've thoroughly covered the basic standard linked list, the singly linked list, but you mentioned variations. Hello Algo touches on these too.
Right.
What other flavors do linked lists come in?
Right, the one we've been discussing with value in just one next reference, that's the singly linked list. It's the foundation.
Okay.
Then there's the circular linked list. It's like a singly linked list, but with one twist.
Yeah.
The next reference of the very last node, the tail node,
Instead of pointing to null,
it points back to the head node,
yeah,
creates a loop, a circle.
no end. What's the advantage of that kind of structure?
Well, a key thing is that since there's no null endpoint, you can effectively start traversing from any node and eventually cycle through all the others and get back to where you started.
Yeah.
Useful for things that need to cycle continuously.
Interesting. Okay, what's the third type?
The third main one is the doubly linked list.
Mm-hmm.
Here, each node gets more complex. It doesn't just have a next reference pointing forward.
It also
has a prev reference pointing backward to the previous node, its predecessor.
so you can go both ways, forwards and backwards through the list easily.
Exactly. Doubly linked lists give you that bidirectional traversal.
Mm.
Super handy in some cases. But remember the trade-offs.
More memory.
Yep. Each node now needs space for the data, the next reference, and the prev reference. So doubly linked lists consume even more memory per node than singly linked lists. Again, you choose based on whether that backwards traversal capability is worth the extra memory cost.
Okay, singly, circular, doubly. Different structures, different trade-offs. Now, connecting this back to the real world, where do we actually see these different types of linked lists being used? What are some common applications?
Oh, they're everywhere, often underpinning other structures you might be more familiar with. Let's take singly linked lists first. They're a very natural fit for implementing stacks, last in, first out, and queues, first in, first out.
How so?
Well, for a stack, you just add and remove elements at the head of the list. Both are O1 operations. For a queue, you might add at the tail and remove from the head again, typically O1 operations, if you keep track of the tail properly. Their efficiency fits the LIFO-FIFO models well.
Makes sense. What else?
They're crucial in hash tables for resolving collisions, using a technique called chaining. If two different keys hash to the same slot in the table.
They collide.
Right. Instead of overwriting, you can attach a linked list to that slot. All the items that hash to that same spot just get added to this list. Searching that specific list might be ON for the list length, but it works well if collisions aren't too frequent.
Clever way to handle clashes.
And in graphs, they're often used for adjacency lists. Each vertex or node in the graph can have a linked list attached to it, and that list contains references to all the other vertices it's directly connected to. For graphs that aren't densely connected, this is usually much more memory efficient than using a big grid and adjacency matrix.
Fascinating. So, simple lists, building complex graphs. Okay, what about the other types? Doubly linked lists.
Doubly linked lists pop up when you really need that ability to go backwards easily. Think about advanced data structures like red-black trees or B trees, the kind used under the hood in databases and file systems. Nodes in these complex trees often need to quickly find their parent node.
Which is like going backwards to the predecessor.
Exactly. So nodes in those structures often contain something very much like a prev pointer, similar to a doubly linked list node.
Okay, that's a bit abstract. Any more everyday examples?
Absolutely. Your web browser history. When you hit the back button or the forward button.
Ah, you're moving through a sequence.
Precisely. A doubly linked list is perfect for that. Each visited page is a node. You have next pointers for going forward and prev pointers for going back. Moving to the immediately previous or next page is an O1 operation.
That's a great example. I can totally picture that now.
Another big one is the LRU algorithm, least recently used. It's super common in caching systems.
Caching, right. Storing frequently used stuff for faster access.
Yeah, and LRU cache needs to do two things really fast.
Yeah.
Find the oldest item, the least recently used one, to kick it out when the cache is full, and move any item that just got access to the front of the line, marking it as the most recently used. A doubly linked list is ideal here. You can keep the most recently used item at the head and the least recently used at the tail. Accessing an item means moving its node to the head. Because it's doubly linked, you can remove that node from anywhere in the middle and reinsert it at the head in O1 time. You don't need to search for the node before it to update pointers. You already have the prev pointer.
Wow. Okay, that O1 move is powerful there. And circular lists, where do they fit?
Circular lists are great for anything that needs to cycle or loop. A classic example is in operating systems for round-robin scheduling.
giving each program a little turn.
Exactly. Processes waiting for the CPU can be put in a circular linked list. The scheduler gives a time slice to the current process, then just follows the next pointer to the next process in the circle, and so on. It naturally cycles through them, ensuring fairness.
A continuous loop of processes getting their turn.
Right. And they can also be used for data buffers, especially for streaming media like audio or video. Imagine a buffer as a circle. Data is written into one part of the circle while it's being read from another part. As the read point chases the right point around the circle, you get smooth, continuous playback.
Very cool. Seeing all these applications really makes the different structures click. They're not just abstract ideas, they're solving real problems in software we use constantly.
Absolutely. There are fundamental tools in the programmer's toolkit.
Okay, let's try and wrap up this deep dive then. We've really dissected the linked list today. We started with its basic structure, those nodes, with values and references, living potentially anywhere in memory.
Contrasting that strongly with the contiguous nature of arrays.
Right. Then we looked at operations. Insertion and deletion, especially in the middle, are remarkably efficient for the linking step O1. But accessing a specific element by position or searching for a value, that's generally linear time, ON.
The opposite trade-offs compared to arrays, typically.
Exactly. We also explored the variations, the standard singly linked list, the looping circular list, and the two-way doubly linked list, noting their specific features and memory costs.
And we tied it all together by looking at a whole range of real-world applications: stacks, queues, hash tables, graphs, browser history, caching algorithms, OS scheduling, data buffers.
It shows just how versatile these structures are. Hopefully this hasn't just been a list of facts, but has given you a really deep, memorable grasp of why linked lists are important and the kinds of problems they excel at solving.
Their real value is that flexibility in memory and the efficiency for dynamic changes, even if it costs something in access speed.
They're absolutely fundamental. So as a final thought for you, our listener, to mull over, as you use software day to day, think about where these seemingly simple chains of nodes, these linked lists, might be working silently behind the scenes. Knowing their strengths and weaknesses, how does that change how you perceive the performance or the design of the apps you rely on?
Yeah. Where else are they hiding?
Something to ponder. Thanks for joining us on this deep dive.